Hello everybody. In this video we are going to look at the solution to the Physics 1 electromagnetic spectrum due right now, number 1. Let's take a look. I just scared the crap out of my entire family. I love it. I love it. Yeah. What was that? No comments from the peanut gallery over there. I know. Yeah, you should see the kids when I do it. Alrighty. That never gets old. It never gets old. All right, let's take a look at the problem. And then I gotta go call a paramedic for my wife because I think she just had a heart attack. All right, and my Emmy just ignored me, by the way. She just ignores me every time I yell. So, all right, here we go. Let's see, the primary colors are red, green, and blue. Based on the wavelengths below, calculate the range of frequencies for each color of light. So I know that my wave speed formula with the speed of light is c, which is my speed of light, is equal to the frequency times the wavelength. So the range for wavelength for the blue portion of the spectrum is from 455 to 492 nanometers. So I need to convert both of those wavelengths to meters. So simply have to put times 10 to the minus ninth onto each one of those. So 455 nanometers will equal 455 times 10 to the minus ninth meters. And the same thing for the upper end of the blue range of the spectrum. 492 nanometers will convert to 492 times 10 to the minus ninth meters. Now to take my wave speed formula and solve that for frequency, I'm going to have the frequency is going to equal the speed of light divided by the wavelength. And my speed of light, as always, my universal speed limit is 3.0 times 10 to the 8th meters per second. When I divide that by my first wavelength of 455 times 10 to the minus ninth nanometers, I am going to have a frequency of 6.59 times 10 to the 14th hertz. Now for the upper range of the spectrum, 3.0 times 10 to the 8th meters per second divided by 492 times 10 to the minus ninth meters will give me a frequency of 6.10 times 10 to the 14th hertz. All right, let's take a look at part B of this problem. By the way, I just asked my wife if she felt bad for you guys because I was shouting, and she said, no, you guys pretty much deserve what you get. So no sympathy for you guys either from her. All righty. So the next portion of the, so what? What'd you say? She's mad because I just threw her under the bus. That's all right. She's gonna get back at me by not leaving me anything in her will. All right, let's see, where was I before I was so rudely interrupted over there? Okay, so what's our next primary color? It's green, and our range of wavelengths for green are 577 nanometers. I'm sorry, it's 520 nanometers to 560 nanometers. So the lower end of the range is 520, and the upper end is 560. And as before, we do have to convert both of those to meters. So to find the frequency for the low end of the range, 520 times 10 to the minus ninth meters, I divide that into my speed of light of 3.0 times 10 to the 8th meters per second, and I will have a frequency of 5.77 times 10 to the 14th hertz. For the upper end of the blue range of the spectrum, I have 560 times 10 to the minus ninth meters, and that will give me a frequency of 5.36 times 10 to the 14th hertz. One more primary color to go, and that color is red, and the range of wavelengths for red are 622 nanometers to the upper end, which is about 780 nanometers, and at that point we're getting into the infrared end of the spectrum. So again, we're going to convert both of those to meters, and to find the frequency for the lower end of my blue range of the electromagnetic spectrum, I'm going to take my speed of light, 3.0 times 10 to the 8th meters per second, divide that by 622 times 10 to the minus ninth meters. That will give me a frequency of 4.82 times 10 to the 14th hertz. And to do that for the upper end of the red range of the spectrum, I'm going to take again my speed of light of 3.0 times 10 to the 8th meters per second and divide that by 780 times 10 to the minus 9th meters, and that will give me a frequency of 3.80 times 10 to the 14th hertz.